Okay. So sequential circuits output not only depends upon the current input, it also depends upon the previous inputs. We see example later how it is changing. Okay. To provide the previous input, so we have to store that output. So a memory element is required in sequential circuits. So here the outputs are changed at particular instance. So there is timing is available. Timing parameters you have to taken into consideration in sequential circuits. So combinational circuit we have learned so far. So you have a nested state. So there is storage elements. So the storage elements will have the previous state. That state is taken as the input, one of the input, and current inputs as another input. So these two combined together produce the output. Okay. So far we have seen the combinational circuit. So when you give the input, it produces the output. That is combinational circuit. Sequential circuit means the previous output is stored in a storage element. That element will produce the output. That is also another input. And normally there is a current input. This is another input. These two inputs determine the output state. So this type of circuits are called sequential circuits. So the basic element of a sequential circuit is latch. So another one is flip-flops. So what is the difference between a latch and a flip-flop? So a latch means it has no timing signals. Timing signal means there is no clock signal. In flip-flop, you have a timing signal. So the circuit shown here is a latch. Here there is no timing signal. Okay. Flip-flop is the basic digital memory circuit. So here it is shown is a latch only. So here in a latch, so inside the latch, what is there means it may be an or NOR gate. So it may be a NOR gate. Hello? Hello? Hello?
Yes, sir.
கேக்குதா? கேக்குதா?
Sir, yes, sir. Yes, sir.
So, latch and flip-flop are the
Sir,
basic
make it
elements
full
in
fledged, sir.
sequential circuit. So inside the latch or flip-flop, you have either NAND gate or NOR gate.
Sir, make it full slide.
Hello?
Sir, make it full screen.
Full screen.
Now, okay, sir. Now, okay, sir.
So the basic element in sequential circuit is either latch or flip-flop. So inside the latch or flip-flop, you have only NAND gates. For that NAND gates also, it is connected back to back. There are two outputs in a latch or flip-flop. One output is Q, another output is Q bar. So the input may be differ according to the flip-flop, but the output is same only. One output is Q, another output is Q bar. This Q and Q bar are complementary. If Q is 1, Q bar is 0. If Q is 0, Q bar is 1. So these are complementary outputs. So a first basic element is SR latch. So this is a SR latch. So what we are doing is, this is a NAND gate. We are giving an input S dash. We are taking an output. That output is taken as input to the another gate. Here another input R dash is given. Here totally there are two inputs. One it is R dash, another one is Q. Here for this NAND gate, one input is S dash, another input is Q dash. Okay. So the output of gate 1 is connected to the input of gate 2, and output of gate 2 is connected to the input of gate 1. Okay. So we are calling this, these transistors AND gates are connected back to back. It means back to back means the output is connected to the input. Both the AND gates are connected as like this. The output is connected to the input of the other gate. Here also the output of the this AND gate is connected to the input of the next gate. So this is the circuit connection of a SR latch. The output may be anything. For a particular instant, we are taking, assume the output of gate Q equal to 1 and Q dash is equal to 0. Q equal to 1 and Q dash is equal to 0. Q1 means it is connected as input to R dash. Okay. So Q1 it is connected to R dash. So this 1 will come here. For NAND gate, the output is 0 only. So this 0 will go here, and here you get an output of 1. Okay. So this state will be continuing. Okay. 1 and 0 output, and input are 0 and 1 for this SR latch. So we take another example. Here 0 and here 1. So 0 will come here. So 0 complement 1 here. 1 will come here. 1 complement 0. So this will remain in the state. The output is 0, 1. Input is 1, 0. Okay. So it is a basic memory cell in a sequential circuit SR latch. So there are two input combinations, either 0, 1 or 1, 0. The output are complementary. So 1 and 0 or 0, 1, 1. So next one is, so we have in the last example, we have seen S dash and R dash. So I want to give S and R. Then what I have to do is, I'm using a NOT gate before. So here it is S dash, here it is R dash. So in order to make it, I want to give S and R, I put a NOT gate before. So I get S here and S dash here. And similarly R here and R dash here. So that is the use of this particular NAND gate used as a NOT gate. So for any flip-flop or latch, you have a truth table. So from this, we have already seen this. If it is 1, 0 means here it is 0, 1. So 1, 0 means here it is output is 0. So this is a truth table for a NAND gate. 0, 0 means 1, 0, 1 means 1, 1, 0 means 1, 1, 1 means 0. For SR latch, both are 0. If, for example, S equal to 0, R equal to 0, both are 0. Then we assume that here 0 and here 1. So 0 will come here, it becomes 1, and 1 will go here. And it will be the same state. For example, so last, it is NAND gate version, okay? It is also NAND gate version. So one input is R, another input is S. Here one input is Q, another input is Q bar. Okay. So I'm writing this table in the blackboard, then only you can understand. Otherwise, so the diagram given is NAND gates. So one input is like this, another input is like this. Here it is S, here it is Q and Q bar. So I am giving input 0 and 0. Previously it was 0, 1, 1. Okay. Before I'm giving the input 0 and 0, there is an input of 0 and 1. So what will happen? So I'm taking this input as first input. 0 and 0, 1. 1 and 0, For NAND gate, 1 and 0, the output is 1. 1 and 0, the output is 1. So once again, this one will come here. So this 1 and 0, the output is 1. This 1, 1 and 0, 1. 1 and 0, 1. 1, 1 is not possible because Q and Q bar are complementary. Q and Q bar are complementary. So this state is not possible. Okay. So you cannot use this. So in SR latch, you have only two states, S and R, Q and Q bar. So if S equal to 0, Q equal to 0. S equal to 1, Q equal to 1. So this condition is called set. This condition is called reset. If S equal to 0, Q equal to 0. So set 0, Q equal to 0. So output is 0 means it is reset. If S equal to 1, Q equal to 1. So it is known as set. So in the previous case, we take S dash and R dash. Now I am taking S and R. So I am getting the output of S equal to 0 means Q equal to 0. So only two states are possible in SR latch. So you cannot use 0 and 0 and 1 and 1. Okay. So it is a basic flip flop. So they modified into a different another flip flop which can use all the four states. When S equal to 0, it makes Q bar equal to 1. So when you give S equal to 0, it automatically makes Q bar equal to 1. So it is known as reset. So when you give 1 and 0, so what it becomes, Q becomes 1. So it is known as set. So in this case, when you give 1, 1, for example, I am giving 0 and 0 is not possible. I am giving 1 and 1. Initially it is 1 and 0. Initially it is 1 and 0. What happens is, so 1 will come here, 1 and 1, 0. So it becomes 0. 1 and 0. For NAND gate, 1 and 0 is 1 into 0, 0. 0 becomes 1. So 1, 1, 0. Okay. So it remains in the same state. So when you give 1 and 1, so it is remains in the previous state. It remains in previous state. So if we give 0 and 0, we give 0 and 0, it is not possible. Not possible. We are calling as undetermined state. Undetermined state. We couldn't find what is the state. So when you give S equal to 0, P equal to 0. That is known as reset. When you give S equal to 1, Q equal to 1. That is known as set. Here S1 means set, here R1 means reset. When both are 1, it will be remain in the previous state. This is for NAND version. NOR version means it is opposite to it. So when you give 0, 0, it will be previous state. So you have to see whether it is a NAND version or NOR version. So depending upon the gate used in the latch, it will differ. Okay. So this is SR latch. SR latch NAND version. So 0, 0 is not allowed, disallowed. So R equal to 1 means reset. S equal to 1 means set. 1, 1 means no change. It will be remain in the previous state. Okay. So what are the methods to trigger the flip-flop? So this clock signal is only available in flip-flop. It is not available in latch. So there are two types of triggering the flip-flop. One it is level triggering, another one is edge triggering. So level triggering means, so if you look at this signal, it is a square signal. So it moves from low to high to low. So here it is moving from low to high. We are calling this portion as a edge. So since it is moving from low to high, we are calling as positive edge. Here it is moving from high to low. So we are calling as negative edge. For this portion, we are calling as a level. It is level 1, it is level 0. For this transition, we are calling as positive edge. This transition, negative edge. This is a level. So when the output changes during this period, level 1 period, we are calling as level triggering. When the output changes during these edges, we are calling as edge triggering. Okay. So level triggering means the circuit will respond to the input only during the level 1. So during the change in their input, if they enable input at active level or high level. Sometimes you can use the flip-flop to trigger at the low level also. Mostly they are used in high level. You can change the connection and you can trigger at low level also. It is possible. This type of triggering is called level triggering. So next one is edge triggering. So it may be positive edge triggering or negative edge triggering. So the output changes to the input when the during the this edge low to high edge we are calling as positive edge. So when the output changes during this positive edge of the clock signal, we are calling as positive triggering. Similarly, this is level triggering. So here the output changes at this level, level 1. So it is called positive level triggering. When the output of the flip-flop changes during this level 0, we are calling as a negative level triggering. So next one is edge triggering. So I told that when the clock signal changes from level 0 to level 1, it is positive edge. And similarly, level 1 to level 0, it is negative edge. So positive edge or rising edge, negative edge or falling edge. We are calling as the edges as positive edge or rising edge of the clock signal or negative edge of the falling edge of the clock signal. So in the positive edge triggering, the flip-flop allows its output to change its response to its input during the rising edge of the clock. So during the rising edge of the clock, so we are calling as positive edge triggering. Similarly, flip-flop will respond only to the falling edge of the clock. It is called negative edge triggering. So next one is, so when we are giving a clock signal, this SR latch becomes SR flip-flop. Whenever you are giving a clock to a latch, it automatically becomes a SR flip-flop. Okay. So here, I have using 4 NAND gates. First 2 NAND gates are used for inversion. So next 2 NAND gates are connected back to back. So as we know that we are not giving clock signal in a flip-flop, output won't change. Okay. Next one. So this S and R, I have told that it is S and R, it is actually S dash, X complement and X complement. Because it is A NAND gate is available here. This is S complement and R complement. S and R. Okay. So SR means, here the draw once again, SR 1 0 0 1 0 0 and 1. So when SN here it is 0 0 here 1 1.
Sir, voice is not hearing, sir.
Yes, yes, yes. I am not speaking now. Okay, okay. Hello? Now it is hearing?
Sir, now it is hearing, sir.
Yes, yes. So when S equal to 0, when S equal to 0, S dash is 1. So 0 1 means When S equal to 0, the output is 0. When S equal to 1, output is also 1. Here it is 0, 1. Okay. So when S equal to 0, 0, here it is 1, 1. So it is will be in previous state. If it is 1, 1, here it is 0, 0. So it is not possible. It is a indefinite, indeterminate state or indefinite state, whatever may be. So in a flip-flops, you should always remember that when both inputs are 0, when both the inputs are 0, the output is would not change. It will be remain in the previous state. When S equal to 0, R equal to 0, it will be remain in the previous state. There is no change in the output. When S equal to 0, S means that R equal to 1. So R is 1. So it is a reset state. When S equal to 1, R equal to 0. So now S equal to 1. So it is a set state. Set state means Q is 1. Reset state means Q equal to 0. Q bar will be 1. Okay. If S and R is 1, 1 means output is, you cannot get the output when you give both the inputs are 1. So there is a disadvantage in this SR flip-flop is when both the inputs are 0, the output is not changing. When both the inputs are 1 means you cannot find what is the output. So it is an invalid state. So to overcome this, they have designed for some other flip-flops. So when you ask what is the disadvantage of SR latch, you have to tell when both the inputs are changed, outputs, when both the inputs are 0, the output is not changing. When both the inputs are 1, the outputs are invalid or undefined. Next one is D latch. So what is inside the D latch? It is only SR latch only. What I am doing is I am connecting the S and R inputs connected together. I am connecting both the inputs together. S and R inputs together. What will happen? It becomes a single input. So we are calling this input as D. And we are calling it as D flip-flop. So if there is clock means it is D flip-flop. If there is no clock means it is D latch. Okay. So it is a D flip-flop because there is a clock is available. Okay. So what happens when you are connecting both inputs together? You cannot give 0, 1 and 1, 0. Okay. When you give 1, both the inputs will be, when you give 1, D equal to 1, both the inputs will be 1. So what it happens? The output won't, so Q becomes 0. Similarly, when you give 1 in both the inputs, Q becomes 1. Okay. So in D flip-flop, you should understand that when you give the input 1, D input 1 means the output becomes Q. There is a output, you have to write the output Q equal to 1. When you give D equal to 0, when you give input 0, Y means because I am giving 0 here. So 0 will come here. There is a inversion available here. Here 0, S means X is 0, R is 1. So I am explaining in more. So this is a D input, this is S input, this is R input. Okay. So when I give D equal to 0, so automatically S is also 0. What will happen to R? It is a inversion. So it becomes 1. So what will happen to Q? It becomes 0. Q bar, it becomes 1. So another input what I can give in D, it is 1. this is equal to 1, R is automatically becomes 0 due to the inversion. So now Q is 1, Q bar is 0. This is the output. This is a truth table for this D flip flop. So these are intermediate states. So I am cancelling this. Okay. So when D equal to 0, Q equal to 0. And D equal to 1, Q equal to 1. Only two states are available in the SR flip flop. Either 0, 1 or 1, 0. These two states are eliminated because of this inversion. So either it is 0, 1 or 1, 0. Okay. So when D equal to 0, Q equal to 0. When D equal to 1, Q equal to 1. So this is the working principle of D latch. SR latch is modified into D latch. Okay. So next one is JK latch. So in the JK latch, what is done is another connection is given. If you look at we are using 4 NAND gates. 3 and 4 NAND gates are same only, same connection only. The first 2 NAND gates, so Q bar is taken in the first NAND gate, and similarly Q is taken in the second NAND gate. So we are changing the inputs S and R to J and K. Okay. So in the first NAND gate you have 3 inputs, second NAND gate you have 3 inputs, third and fourth NAND gate you have only 2 inputs. By connecting this method, what is possible is you can use the state 1 1. You can use the state 1 1. So that is possible. So when you doesn't give any clock, the output won't change. The clock, if you switch off the clock means the output won't change. So C equal to 0 means whatever the input J and K, the output will remain in the previous state Q, no change. Next one is 0 0. When J equal to 0, K equal to 0. Now we are applying clock. What happens? Both the inputs are 0. The output will remain in the previous state. No change. Okay. Now 0 1. J equal to 0. So J input is previously S input. So J equal to 0 means Q is also equal to 0. So it is a reset state. Next one, J1, K0. So J equal to 1 means S equal to 1. So Q equal to 1. So it is a set state. Finally 1 1. So when you give 1 1, what it happens means due to this another new interconnection, so the whatever output previously will toggle. So whatever output is previously will toggle. If it is previously 0 1 means now it becomes 1 0. If it is previously 1 0 means it becomes 0 1. So whatever previous output will toggle. So we are mentioning as Q bar. So it is called toggle mode. So in JK flip flop, you can give 0 0 when there is no change in the output. If we give 0 1, it is called reset. 1 0, it is called set. 1 1 means toggle mode. The output will change its values. Q will change to Q bar and Q bar will change to Q. That is known as toggle mode. So what is race around condition in flip flop? So when you are giving 1 1, so in inputs of JK flip flop and Q is 0. Okay. So after a time interval TP equal to the propagation delay of the NAND gates, the output will change into Q equal to 1. Now J equal to 1, K equal to 1 and Q is also equal to 1. If the duration of the clock pulse is greater than propagation delay Tp, another time interval of Tp output will change back to Q equal to 0. So sometimes this may be happen in flip flop. So when you give the input J equal to 1 and K equal to 1, we say that it is toggle mode. So previously it is 0 means now it becomes 1. That is known as toggle mode. So there is a problem when The time interval means propagation delay, the changing period Tp, 0 to 1 is called changing period Tp. When it is equal to the propagation delay of that NAND gates. So what is propagation delay? Propagation delay means when you are giving the input, the output changes. The time interval between the input applied, the output changes is called propagation delay. So when the transition time Tp is equal to the propagation delay of the NAND gates, the output will once again change to another state. So this will continuously happen, and this condition is called race around condition. For in order to avoid this race around condition, you have to make that. So you have to reduce the clock pulse. Then you have to reduce the clock pulse duration less than the propagation delay of the flip flop. This is very difficult in flip flop. So they mostly go to master slave flip flop. Master slave flip flop means it has two flip flops. So this is a clock pulse. So the output changes after a particular time interval. So yeah, we told that the output changes at the icing edge of the clock pulse or negative, positive edge or negative edge. But actually, it will happen on a certain time interval in very few milliseconds or microseconds. The time interval of applying the clock pulse, the output obtained in the output time interval is known as a surround condition. So latches are transparent. So transparent means it depends upon the input. So the output changes only on the input. So this will cause many synchronization problems. Mostly latches are not used for storing the memory. So they are using only flip-flops because the output should change at a particular instant of time, not randomly. So the flip-flop are sent to be edge triggered or level triggered. Edge triggered means it may be positive edge triggering or negative edge triggering. Next one is level trigger, level 0 or level 1 trigger. So this is edge triggering flip-flops. So SR flip-flop is given. So there is a circuit given, a capacitor and a diode and a resistor. So this capacitor will remove the unwanted noises, and these resistors are used to limit the current. Diode is used to convert the conventional current. Okay. So flip flop when you are giving not giving clock, the output remains there is no change. So in the edge ticket flip flop, the level 1 there is no change in the output. During the negative edge, this is a positive edge flip flop. During the negative edge, there is no change. During the positive edge only you have changes. The positive edges, so positive edges, during the positive edge, when you give input 0 and 0, there is no change. 0 and 1 means reset, 1 0 means set, and if it is 1 1, it is a invalid state in a circle. So next one is D flip flop. Yes, and R inputs are connected to the D flip flop. So no change. If there is the clock is not given, if you give clock, and if you are not given any input in the first bike, you have no change. Next one, during the negative edge also there is no change. During the positive edge, and the input is D input. D input is 0. It follows the D input. The input is positive edge and D input is 1 means the output becomes 1. So the Q follows the D input. Next one is VK flip flop. The clock is 0, there is no change in the output. The clock is 1, there is no change in the output. During the negative edge, there is no change in the output. During the positive edge and J equal to 0, K equal to 0, no change. During the positive edge, K0, K1 reset. During the positive edge, 1 0 means it is set, 1 1 means it is toggle. For T flip flop, we are calling it toggle flip flop. So this T flip flop is constructed by using JK flip flop. We are connecting together the both inputs T and J and K. Totally it is two animals. T and J and K. So when you here also when you are giving no not giving any clock pulse, output is 0. When 1 is given, there is no output. When you give negative edge also not possible. During the positive edge, when you give input 0, J and K will be 0. When both are 0 means output won't change. Next case, when input is 1, T equal to 1, J and K are 1, the output will toggle. Okay. So this is the condition for toggle flip flop. So what is counter? Counter is a digital sequential circuit which will count the number of events. So we are calling as counters. These are classified into two types, synchronous and asynchronous counters. So synchronous counter means so the timing clock signal is applied to all the flip-flops at the same time. That is known as synchronous counter. So asynchronous counter means all the flip-flops, the clock signal is not same. The clock signals are same only in the synchronous counters. So this counter, first counter is a asynchronous counter. So all the flip-flops are not hooked to the same clock. All the flip-flops are not connected to the same clock. So this is a clock signal. So Q is the clock signal follows them. It is 1 and it goes to high. After 12 p.m. it goes low and so on. So Q bar 8 is the inverse process. So this asynchronous counters we are calling as ripple counters because one flip-flop respond only, then next flip-flop can respond. So all the flip-flops cannot be responded at the same time. That is known as ripple counter and this is known as rippling effect. So in a ripple counter, a flip-flop output transition serves as a source for triggering other flip-flops. In a ripple counter, a flip-flop output transition serves as a source for triggering other flip-flops. If we look at this diagram, I will see a diagram later. So this is a clock. Q0 is the first flip-flop output. Q1 is the second flip-flop output. For second flip-flop Q1, for second flip-flop, flip-flop 1, you have to take input from the previous flip-flop output. So here it is a negative edge triggered flip-flop. So clock signal is given to the first flip-flop. During every negative edge signal, here a positive edge signal. So during the positive edge, so the clock is translating 0 to 1, 1 to 0. Every edges are taken. 0 to 1 taken 0. 1 is same 0. 1 to 0 we are taking the transition. So first flip-flop during the positive edge of the clock pulse it changes its output. During the positive edge of the clock pulse it changes its output. That is Q0. For second flip flop, the first flip flop negative edge it changes. If you look at this, Y means we look at the diagram. Here, the clock will have a inversion. Okay. So clock has inversion means positive edge means actually it is negative edge it is trigger. So it having inversion means it is positive edge it is triggering. So remaining things you see it is a negative edge triggering. 1 to 0 negative edge. So it changes. Here 1 to 0 negative edge changes. 1 to 0 negative edge changes. 1 to 0 negative edge 0. 1 to 0 negative edge 0. 0 to 1 here negative edge. Here there is a problem. Okay. So if we look at this counter, you have two flip flops. So one flip flop is here, another flip flop is here. So these two flip flops are connected together in such a manner it becomes 2-bit counter. So first flip flop output is connected as input to the second flip flop. Okay. So Q0 has a period of 2t, Q1 has a period of 4t. So after producing the flip flop output T1, they will produce output on Q1. Okay. So the n flip flops, the period is 2 power. So in the ripple counter, it may be a 2-bit ripple counter, 3-bit, 4-bit, or so on. So every bit it may be either a 1 or it may be 0. So countdown counter means it will join with the maximum value and slowly starting and reducing by 1 and it finally reaches 0. So binary counter, BCD counter means it will count from 0 to 9 and eventually it starts from 0 to the 4-bit of counter. So it is a ripple counter. So first output is taken C, second output is taken to C, third output is taken to. So here the output is taken from the flip flop. Here also taken, here also taken. So when this first flip flop changes its output for every clock pulse. So Q0 is given as the input to the second clock pulse. So second flip flop will changes its output when the clock pulse changing from positive to negative. Similarly, third flip flop Q2 output depends upon the clock pulse of the Q1. So this is a circuit for a 4-bit ripple counter Q0 to Q3. So two sequences will start from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, up to 15. So countdown counter means it will start from 15 and slowly reaches 0. So initially you have all. So in the binary down counter, so initial output is 1, 1, 1, 1. For this you have to take the output, the complement, not in the cube. Same circuit, you have to take the output in Q bar, Q1 bar, Q2 bar, and Q3 bar. So this is down counter. So counter means you have to take the output as a Q. Down counter means you have to take the output as Q bar. So depending upon the connection you have given, you can do up counter or down counter. So next one is ring counter. So before going to ring counter, what is a counter, what is a shift register, and so on. So counter is a sequential circuit. Every counter has many flip-flops. It may be a single flip-flop, or two flip-flops, three flip-flops, four flip-flops, and so on. So you have to connect the flip-flops in serially. You have to give serious connection, and then you attach the device what you are going to work. So shift registers are used to store only for digital data. So they are group of flip-flops connected in a chain. So the output from one flip-flop becomes the input of next flip-flop. So ring counter is also a shift register. The last flip-flop output is connected to the first flip-flop input. That is known as ring counter. We see how it is working. The operation of ring counter. We look at this. It is a 4-bit ring counter A, B, C, D. Last flip-flop output is connected as input to the first flip-flop. So this process is continuous. For example, initially all the flip-flops are in ring counter. So you have to make reset all the counters. So before applying the class pulse, you have to apply the preset pulse to make the flip-flop send value 1 to the ring counter set. For each class signal, data circulates all the 4 flip-flop stages of the ring counter. So initially all the flip-flop counters are reset by using the reset button. Then you have to use the class pulse using the preset pulse. Using the preset pulse, which assigns the value 1 to the ring counter circuit. Then you are doing every clock signal and you get the output. So it will continuously move from one flip-flop to the next flip-flop, and it is in a circulation fashion. So we are calling it a ring counter. So ring counter is similar to that of the shift register connected in series. So it is a 4-stage Johnson counter, similar to shift register. The data inputs are D0, D1, D2, D3. So ring counter is similar to soft registers connected in home. By passing the reset signal, all the flip-flops will become 0. When the preset is applied to the ring counter, the input of the circuit for a particular flip-flop output becomes 1. For example, I am giving the input, okay, I am presetting the stage to 1. The remaining flip-flop is just 0. So I am giving a input 1 to the first flip-flop by using the preset input. So what is the use of preset input means? It is a master input, you can change any value in the answer paper. Okay, that is known as preset input. So when you apply preset in first flip-flop, it becomes 1. Remaining flip-flops, it is 0. Now you are applying a clock signal. So 1 will move from first flip-flop to second flip-flop, second flip-flop to third flip-flop, third to 4, and finally it comes to the output. So this is known as circular fashion. So we normally do this type of ring counter. For example, the flip-flop A is set to 1. So all other outputs are 0. So after giving a clock pulse, so what it will happen is 1 will come here, remaining are 0. 1, 0, 0, 0. So after giving another clock pulse, so here it becomes 0. Here it is become 1, 0, 0. And next stage 0, 0, 1, 0. And finally, this one will go here, 0, 0, 0, 1. And 1 will come once again here. So truth table of a 4-bit ring counter, initially Q0 is 1. This one will go to Q1, Q1 to Q2, Q2 to Q3, and once again it will come to the Q0. The circulation type of data. That is known as ring counter. For the ring counter, initially we are making all the flip-flops 0 by using the clear input. Then after that, you have to give a clear equal to 1. Then all the counter starts its operation. For one clock signal, the counter starts its operation, and next clock signal, the counter again resets to 0, 0, 0. Encounter has 4 sequence: 0, 0, 0, 1 or 0, 0, 0, 1, 0, 0, 0, 1, 0, and finally 0. So this is the timing diagram of your encounter. So look at this diagram. This is the clock signal. Initially, one is given in the input by reset signal. It does not normally happen. It is injected. It is included in the A flip-flop. Okay. Now, during the negative edge of this clock pulse, P signal will. During the negative edge of this clock pulse, P signal will start. P signal will start. So after this, P signal is not responding. So it is 0 only. So this one data is moving from one flip-flop to next flip-flop. One signal is moving from one flip-flop to next flip-flop continuously. As the data is moving through the flip-flops in a serial fashion, we are calling as a register called ring register. Okay, this register is called ring register. So what is the advantages? You can implement this ring counter either by D flip-flop or JK flip-flop. JK flip-flop, you have to connect both inputs together. So it is a self-decoding circuit. So you can do it by your own. It takes time. Then disadvantage is it can use only 15 states. You cannot move beyond 15 states. So what are the applications of ring counters? Ring counters are used to count the data in a continuous loop. They are also detect various number values and various patterns with a set of information and A and R are logics to the encounter circuits. Two stage, three stage, four stage encounters. Encounters are widely used in many applications. So another application of this encounter is Johnson counter. It is a slight modification of this encounter. We see Johnson counter in the next PPT. So we know that binary counter it has number of flip-flops. Every flip-flop has two states, 0 and 1. Minimum is two, and only it will be regarding as a counter. If it is only one flip-flop, it is a 1-bit flip-flop. It is not a counter. Okay. Counter should have at least two flip-flops with a clocked one. Okay. There are two types of counters, either synchronous or asynchronous. First synchronous counter uses a single clock at a first stage. So synchronous counters, asynchronous counters are classification. Synchronous counter means the clock is given to all the flip-flops at the same time. Asynchronous counter means only the first flip-flop we are giving the clock. Remaining flip-flops we are taking the output of the previous flip-flop that is connected to the clock. So we are calling this Johnson counter as twisted ring counters. So what is twisted ring counter? So in a ring counter, we take the output of the last flip-flop. So we have four flip-flops, we take the output of the last flip-flop. So this then we making presetting the first flip-flop 1. We are externally injecting the input 1 to the output by methods. For the preset method. This one will rotate through every flip-flop. For every clock pulse, it will move to the next flip-flop. So this is known as ring counter. So twisted ring counter means instead of taking the output Q output of the last flip-flop, we have to take Q bar of the output of the last flip-flop. The only difference is instead of Q, we are taking Q bar. Okay. To the first input of the flip-flop. So this is the connection for the Johnson counter. You have four flip-flops. All the clocks are connected together. So it is a synchronous circuit. Then if you look at the diagram, the Q bar output of the last flip-flop is connected as D input to the first flip-flop. Q bar output is the last flip-flop is connected as input to the first flip-flop. So here single clear is not possible. You have to do multiplex clear because this twisted ring counter may produce more outputs. So in a ring counter you have only one output. The one will be available in any one of the flip-flop. But a twisted ring counters or Johnson counter will have more outputs. You have to clear all the flip-flops simultaneously. So first, in order to operate, you have to first give a low input clear, and so you have to clear all the flip-flops. Okay. Then what will happen for the first clock pulse? The final output Q bar will be 1. That is fed as input to the first flip-flop. During the next clock pulse, that one will move crossing the first flip-flop and it will reach the second flip-flop. So the one will appear at the output of the second flip-flop. This process is continuous, and at one stage, all the flip-flop output is 1. So now, when all the flip-flop output is 1, the final flip-flop output is 0 now. So that is given as input to the first flip-flop. So flip-flop first input becomes 0. So this process is continuous, and at one stage, all the flip-flops will become all 0. So when all the flip-flops is 0, the last flip-flop Q bar output is 1. So it is given as input to the first flip-flop. So this process is continuous. So if we look at the truth table of this diagram, initially all the flip-flops are 0. Q0, Q1, Q2, Q3. So second state. So Q3 bar is 1 now. It is given as the input to the first flip-flop. So Q bar will be Q0 will be 1, remaining outputs are 0. So next clock pulse. So the Q0 output is input to the next flip-flop. So Q1 output is also 1. Q0 output is also 1 because Q3 bar is 0. Q3 bar is 1. So 1, 1, 0, 0. Now Q1 is input to the Q2. So this one will move to the Q2 output. Q0 will move to Q1. Q3 bar is 1. So Q0 is also 1. So 1, 1, 1, 0. Now once again, Q3 bar is fed as input to the Q0. So Q0 is 1. Q0 move to Q1, 1. Q1 move to Q2, 1. Q2 move to Q3, 1. So all ones. So at the state of 4, you get all ones. So when you're getting all ones, now Q3 bar is 0. When the state of all 1, Q3 bar is 0. So the Q3 bar is input to the first flip-flop. So Q0 becomes 0, remaining 1. So in next state, Q0 goes to Q1. So 0, 0, 1, 1. Next state 0, 0, 0, 1. Next state 0, 0, 0, 0. This is the first state. So once again, these 0 to 7 states will repeat continuously. So one flip-flop will have one high output. Next state 2 flip-flop. Next state 3 flip-flop. Next state all flip-flops. Once again, it goes to 3 flip-flops high, 2 flip-flops high, 1 flip-flop high, and low. So this process is continuous in a twisted ring or Johnson counter. Okay. So when you consider the waveform, so this is the clock signal. So during the first clock signal, all are 0. So during the next clock signal, so here they are taken positive integrating. Q naught output becomes high. So this is remains high only for 4 states from the 2 to 6. So Q1 will become high at the when Q naught output is given as the input. So it will be remain for 4 states, 3 to 7. So Q2 will be high during this given as the input. So it will be high from 4 to 8. Q3 will be high at 5 and it will be low at 9. So this is a timing diagram for a 4-bit twisted ring counter or Johnson counter. So in ring counter, it will be only one clock signal. So one clock signal, it will go out. So in a Johnson counter, it will be remain high for 4 states. For example, it is a 5-bit ring counter, it will be remain for 5 states. Okay. So depending upon the number of flip-flops, this waveform also changes. So if they mention how many bits, you have to draw the corresponding timing diagram. If I ask you 3-bit run counter, you have to draw only 3 flip-flops. You eliminate this. This output is taken as input to the D flip-flop. And similarly, the truth table, you have no Q3, only up to Q2. So the states will be only from 0, 1, 2, 3, 4. Once again, it becomes 0. So it has only 3 states. So 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1. So after this state, it becomes, there is no this state, 4th state is not there. So it becomes 0, 1, 1, 0, 0, 1, and 0, 0, 0. This state is not available. Both state as well as 0th state will not be available. So this will eliminate 2 states. So it has three flip-flop means it has 6 states. Okay. So in the timing diagram also, here it starts from 2 and it will end in 5, 3 and 6, 4 and 7, 5 and 8. So depending upon the number of flip-flops in the counter, you have to draw the corresponding truth table, corresponding waveform, and corresponding circuit connection. If they doesn't mention any bit, draw any you can draw any bits. They mention 3 bits or 5 bits or 2 bits, you have to draw correspondingly. They are asked to draw 2 bits Johnson counter, you have to draw only 2 flip-flops. They are 5 bits, you have to draw 5 flip-flops. The last flip-flop output Q bar should be taken as input to the first flip-flop D input. Okay. Then you have to draw the corresponding truth table and you have to draw the corresponding timing diagram. It is very, very important. This is all about Johnson counter. So Johnson counter is a modified ring counter. The output from the last stage, the inversion is taken and fed back as input to the first stage. The pattern of bits are equal in length and twice the length of the circuit. This is not needed. So it is used in some specialized applications, decay counter, digital to analog conversion. So another topic is shift register. This is also very important. So shift register is a memory element. So it will store the data as well as it will move the data by one location. For example, I have a 4-bit shift register means it can store 4-bit data as well as it can move the data by 1 bit when you are applying a clock pulse. Okay. Shift register is also another type of sequential logic circuit that is used for storage and it is used for the transfer of data in the form of binary numbers and it will shift the data for every clock cycle. So we are calling as shift register. So in the shift register, we are using only D-type latches. So D-type flip-flops are D-type latches. For each bit connected together in a serial fashion or parallel fashion. That is known as the daisy chain arrangement. From output from one data goes to the output of the input to the next data and so on. So you can fed the data, you can give the input either serially or parallelly. So the data bits can be fed in or out. You can give the data input or you can take the data output either serially or you can take parallelly. You can either shift right or you can shift left. So there are four options. You can take the input, you can fed the input, you can shift right, you can shift left. These are the four possible operations you can done in a shift register. So number of individual data latches to make a shift register is number of bits you have to store. For example, I want to store a 8-bit data, you have to take 8-bit flip-flop. Nowadays, there is shift register ICs are available. No need to connect flip-flops. Shift register IC is itself available in the market. So this shift register IC has several inputs. So one of the input is set input, another input is reset input. So if we give set input 1 means all the flip-flop output will be 1. If we give reset input 1 means so it will make all the outputs 0. That is known as set input and reset input. Shift register IC are available in the market. So these shift registers operate in 4 modes. So what are the 4 modes means? We already told that we can fed the data serially or parallelly. You can move the data outside serially or parallelly. So four operations are serial in, serial out, parallel in, parallel out, serial in, parallel out, serial out, parallel in, serial out. These are the four possible combinations. First one is serial in, parallel out. You have to give the data serially. So you have to fed the data one by one at the input. But the data, the output you can take at the same time. If I have 4 parallel data, I can take 4 data output at the same time. So next operation is serial in, serial out, SISO. Here the input, the data is given one by one. Output is also taken one by one. So this can be, you can shift left or you can shift right. So next one is parallel in, serial out. So all the input data to all the flip-flops are connected, given simultaneously. The output is taken one by one by using the clock. That is known as parallel in, serial out. Finally, parallel in, parallel out. So all the data inputs are given simultaneously. After one clock pulse, all the data outputs are taken simultaneously. Okay. So first connection, serial in, parallel out, SIPO. So serial in means only one input. So first flip-flop has a input, D input, serial data in. So other has only outputs. These are outputs. These are parallel outputs. Okay. What I am doing is I am giving clock common. Initially, I may clear all the flip-flops by using the clear input. So all the flip-flops become 0. Next, I am giving the input at the D flip-flop. So for the first clock pulse, first flip-flop, A flip-flop will produce output. The remaining flip-flops will have its output as 0. The second data is fed at the input. So first data is available in QA. It is given input to flip-flop B. The QA output will go to QB and second input will arrive at QA. So next clock pulse, QB will go to QC, QA will go to QB, third input will arrive at QA. Next clock pulse, QC will go to QD, QB will go to QC, QA will go to QB, and fourth input will be available at the QA. So after 4 clock pulse, I get all the outputs. This is known as serial in, parallel output. So there is only one input. There are 4 outputs. In order to get the 4 data, I have to wait for 4 clock pulse. Then only I get all the data. For 1 clock pulse, I get only 1 bit. So after 4 clock pulse, I get all the data. Since there is 4 flip-flops, so we can only get 4 outputs. So this is serial in parallel out shift register. So how it is working? So initially all the flip-flops I'm resetting. So resetting means I'm clearing the flip-flops. It becomes zero, logic level zero. Okay. So next one, I'm giving a input one at the first flip-flop. At the first clock pulse, it will be available at the QA. QA will become high one. All the outputs are still at zero. Now the data input. Now I am making the data input zero. So what it happens? QA becomes zero, QB becomes one. QA becomes zero, QB becomes one, and remaining will be in the same state, zero state only. So in the next clock pulse, I am making input as one. Now QA becomes one, QB becomes zero, QC becomes one. Finally, I make D input as 0. Now QA becomes 0, QB 1, QC 0, QD 1. Now I get all the outputs. The output is 0, 1, 0, 1. So I get all the outputs. And finally, I get, initially, if you see the truth table, you can understand. So initially, I'm making all the flip-flops 0, 0, 0, 0, 0, 0. So at the first clock pulse, at the end of the first clock pulse, I'm giving input D equal to 1. So the D will arrive at QA. Remaining inputs are 0 only. So second clock pulse, now I'm making input 0. So it becomes 0. So here this one will move here. Actually this QB will move here, QC will move here. 0, 0. So I'm making the D input 0 afterwards. Now 0 becomes 0. This 0 move here, 1 move here, 0 move here. Next one, 0 only input. So 0, 0 here, 0 here, 1 here. Once again 0. So 0, 0, 0, 0, 0. So this is the operation of a serial input, parallel output. Parallel output means you can take all the outputs simultaneously. Serial input means you can give input one by one. So at least 4 clock pulses are needed to get the full output for a 4-bit shift register. Okay. So this is the timing diagram for the particular input. So first D equal to 1, remaining time D equal to 0. So this 1 will be moving every time to the next flip-flop for every clock pulse. Next one is serial in, serial out. So here there is no parallel output. So this is very similar to the above example, except that there is no parallel output, only serial output. If you look at this, there is only serial output. So you have to wait 4 clock pulse in order to get the. So in the last example, you will get 4 clock pulse. In this example, I'm giving the first data. First clock pulse will be arrived here. Second clock pulse, third, fourth. The fourth clock pulse, I get the first input output. First input, I get at the output. So next clock pulse, I get the second input. Next clock pulse, I get the third input. Next clock pulse, I get the fourth input. So you require 4 plus 3. 7 clock pulses are required to get a 4-bit data in order to cross the 4-bit shift register in serial in, serial out. So here they have finished. So I will explain the board. Sir, attendance note பண்ணி மெசேஜ் பண்ணி.
சார் உங்களுக்கு அட்டெண்டன்ஸ் சென்ட் பண்ணியாச்சு சார்.
சரி.
ஓகே.
I take 3 shift register, 3 bits shift register. So this is A flip flop, this is B flip flop, this is C flip flop. So this is input D in. So this is D out. So D in, QA, QB, QC. SI, SO. SI, SO. So I have three inputs, 3-bit input. Okay. My input is 101. Okay. So first I have to give only one because it is a single input. So one. So zeroth clock pulse. We write the clock pulse also. Clock. Zeroth clock pulse. We will reset all the flip flops. So it is zero. So during the clock pulse, I am not giving any clock pulse. So I am using zeroth clock pulse. So the input is one. The output is all output are zero. So after applying the clock pulse, first clock pulse, this D in will arrive here. QA become 1, these two remains 0. Next I have to give the data 0. So second clock pulse, this 0 will arrive here, 1 will move here, this 0 will move here. Next I have to give the data 1. 1. So this 1 will come here, 1 will come here, 0 here, 1 will come here. This is third clock pulse. So in the third clock pulse, this is the output. You see, I get only 1. I want the data 101. So I have to go for that. Here there is no data. Okay. So it is undefined. So I leave it undefined. So now it is 1, 0, fourth clock pulse. So here also undefined. This undefined come here. 1. Fifth clock pulse. So I get 0, 1 during the fifth clock pulse. Here fourth, here third clock pulse. So in the last example, for a 4-bit data, I require 4 clock pulses only. Here for a 3-bit data, I require 5 clock pulses. For 3-bit data, I require 5 clock pulses to come out from the fifth register. 5 clock pulses are required. Okay. In SISO. In SIPO, you require only for 3-bit data, you require only 3 clock pulses. 3. So these two are serial input. Another one is PASO and PAPO. First I explain PASO. In PASO, I'm taking 3-bit shift register. ABC. So parallel it means I'm setting all the flip flops. These are in set connection. Set connection. Similarly, you have a clear connection, there is a set connection. So this is the input. The set input is the input. This is the output. Okay. So parallel input means all the inputs are given at the same time. So I am giving DA, DB, DC. DA, DB, DC. Same time, 101. You have QA, QB, QC. So clock pulse, next we have to. So in the 0th clock pulse, all are 0. Actually we make reset. Okay. Next, I'm giving a clock pulse. So I'm giving all the inputs simultaneously, parallelly. So QA becomes 1, since DA is 1. DB is 0, QB is 0, EC is 1, so QC is 1. Now, I have no data here, so I put dash here. So, but in the output, I get only 1. The first clock pulse, I get only 1. So, next clock pulse I am applying. So, they have no data. So, I am removing this. I am making this connection. I am cutting out this connection. So, here there is a indefinite state in DA. I am not giving any data. But there is a data here. This QA is input to the flip flop. So, this 1 will arrive here. This 0 will arrive here. So, in the second clock pulse, I get 0. Now, yeah, it doesn't have any data, so this will move here, this will move here. So 3. The third clock pulse, I get that. The third clock pulse, I get that. So in PASO also, we get 3 clock pulse. If it is SASO, it is 5 clock pulse. SAPO, 3 clock pulse. Here also 3 clock. So another connection is uh, parallel in parallel out. Parallel in parallel out. Right? Here there is no connection between the flip-flops. If you look at this, there is no connection between the flip-flops. They are individual flip-flops. These are individual flip-flops. There is no connection between one flip-flop to the next flip-flop. In parallel out connection. Okay. ABC. So I'm giving 101 parallelly. You get 101 simultaneously. So in the first clock pulse, after applying the first clock pulse, whatever input you get at the output. So one clock pulse you can transmit all the data. So that is known as parallel in, parallel out. So totally there are 4 modes of operation: serial in, serial out, serial in, parallel in, serial out, and parallel in, parallel out. So if we ask shift register, you have to explain all these 4 operations. For today's class, we have seen what is a flip-flop, what is sequential circuits, what is a counter, shift register, ring counter, Johnson counter. Next class, there is some design counters. You can design a counter. You have to design a asynchronous counter. You have to design a synchronous counter. There are some design problems are there. It is in K3 level. So we have to solve the problems in the next class. Then we move to the A to D conversion and D to A conversion. A to D conversion and D to A conversion. That's all from the digital electronic circuits. So next week we will complete the unit 3. Then next week itself we have a unit test 2. I think so. It will start on November 1st week. Unit test 2. So the class may be extended for a week. Maybe your final class may be ended on November 18 and so on. So November 1st week you have a exam unit test 2. So for the unit test 2, you have digital electronics portion. So in the portion you have to study, you have to, theory part is you have to write any flip-flop, shift register, ring counter, chance of counter, A to D, D to A conversion. These are theory part. You have to design counters, there are problems. You have to design a combinational circuit, or you have to simplify the equation. These are problems. So this unit also you have both theory as well as problems. So next unit is communication systems. It is fully theory, there is no problem. Full theory. So next unit is full theory. So in this unit you have theory as well as design problems are there. You have to simplify the Boolean equation, or you have to design a combinational circuit, you have to design a counter, like this. So you have unit test on November 1st week. Unit test 2. You have to give a assignment also, assignment 2. So today not problem. I will post the assignment on Saturday. So you have to complete the assignment before the unit test commences. So assignment here is 5 marks. Unit test here is 5 marks. Mohammed Ijaz doesn't contact me so far. So he doesn't want 10 marks. I think so. So you complete the assignment 2 and you study well for the unit test 2 also. So next class we see how to design counters, and we see how to convert the analog signal into digital signal and digital signal to analog signal. So next week your portion will be unit test 2 portion will be completed.